Hi, my name is Dan Alvarez. I'm Chief Technology Officer of ReCirc, and today I'd like to talk to you a little bit about some work we've been doing recently on titanium nitride ALD, where we're comparing um, hydrazine to ammonia. This is a follow-up to some work we did a few years back. I'd like to thank my collaborators at our parent company in Japan, Taiyo Nippon Sanso, Andachi-san, Tsuchibuchi-san, Suzuki-san, and Murata-san, who did most of the work that I'll be talking about here. A few years back, we saw a need for thermal ALD use with hydrazine, where there was an increasing need for low temperature nitride deposition. And we've seen an increasing need over the years where some of the primary films of interest are titanium nitride for electrodes and barrier layers, silicon nitride sidewalls, and for other 3D NAND applications, as well as more recently aluminum nitride heat spreaders. I've seen a lot of interest from several different collaborators. In these instances, ALD with ammonia is challenging due to reduced thermal budgets, or especially for titanium nitride, once you get below about 400 C, ammonia doesn't react very well to form titanium nitride from traditional methods. Some people have demonstrated in the literature that plasma methods do work, but they can have some difficulties with high aspect ratio films, such as which might be used in 3D NAND. 3D NAND or DRAM, where there's a lack of conformality of the film, not just in film thickness, but even with equivalent film thickness. Sometimes there's variation from top to bottom in film properties. So why did we choose gas phase hydrazine? If you just look at some of the thermodynamics here for hydrazine versus ammonia, we were given early on an initial target of 300 C by one of our collaborators. And if you look at the thermodynamics at that temperature, the delta H of titanium tetrachloride plus hydrazine is still negative at negative 40 kilojoules per mole at that 300 degrees temperature, whereas the delta H for ammonia goes positive and is no longer favorable at 117 kilojoules per mole. So that gave us an indication even before we started that reaction with hydrazine could lead to much better results for reduced thermal budgets. There's a question of hydrazine safety that has come up, where hydrazine has a long history of being used as rocket fuel, and we had to make sure we had a very safe way to deliver it. So what we've done is we take ultra high purity anhydrous hydrazine and we take it through several additional purification steps to remove water down to very low levels, which is the topic of another talk. But we then take the anhydrous hydrazine and we stabilize it by mixing it with a proprietary solvent. And what the solvent does is it stabilizes the material and makes it a little bit safer, where it could then be used, this mixture can then be used either with a carrier gas or with vacuum draw to take the hydrazine molecules to the process chamber, where the solvent remains behind in the ampule and does not enter the gas stream. Where in this particular case, we've chosen a solvent that's really more like a viscous oil, has extremely low vapor pressure, where if you tried to measure solvent in the gas stream, you're down around 1 to 2 part per billion. What this buys us from a safety standpoint is we're able to raise the flash point of the mixture, which leads to a much better safety classification from the standpoint of having lower safety numbers. If you look at the United States Fire Code for just your anhydrous hydrazine, you see that it has a 432 rating, whereas if you look at the US Fire Code for our formulation, it has a 321, and reducing it by this amount has enabled us to enter into many different facilities, large company collaborators, as well as universities and smaller labs. So with the solvent-based delivery of anhydrous hydrazine, we found that we do lower the vapor pressure a little bit, but it's 10 to 12 torr versus 14 to 16 torr for hydrazine by itself. However, it's still plenty of vapor pressure to do ALD, where if just at ambient conditions you get about 20,000 parts per million, which is equivalent to about 2% hydrazine in a nitrogen stream. And I wanted to mention some early work that we did in this area. The work was done by who's now Dr. Stephen Wolf, who was a student at the time in Professor Andy Kummel's lab at UC San Diego, where in some initial studies in comparing hydrazine to ammonia at 300C and 400C, they basically found that hydrazine gives at 300C, which is here at 592, gives similar resistivity results to ammonia at 400C, which they found up around 555. So you basically gain 100 degrees by going from hydrazine to, going from ammonia to hydrazine, which 100 degrees is very significant with today's restricted thermal budgets. They also noted an improvement at 400C in hydrazine versus ammonia, and at 300C the ammonia is basically not usable. In the current study, we wanted to expand on this work a little bit more, where we wanted to look at a little bit broader temperature window, as well as look at some of the other properties a little bit more closely. So the study was, very similar, just a little bit more broader in scope. We also looked at varying thicknesses of ALD cycles. In the current study, we used a little bit more crude of a reactor system, where it was basically a tube furnace where we built our own ALD manifolding to go around it in order to perform the ALD sequence. One of the drawbacks here was this tube furnace does have a fairly large volume, which led to some fairly high pulse times that were needed in ALD because of this large volume. Here's the titanium tetrachloride saturation curve. You see it saturates relatively quickly, a little bit over 1 second, but you see a fairly flat ALD curve in this region where the 250 is the highest, and then we have hydrazine at the other 350 and 300 in the other curves. Looking at the nitrogen source saturation curve, for hydrazine, you'd first note a little bit higher growth rate, but in addition to that, you see a relatively soft saturation, but it does saturate, whereas ammonia, you also see a soft saturation, maybe even more soft, where this is not quite flat yet after 10 seconds of ammonia pulse time. Looking at the titanium nitride thickness as a function of ALD cycles, we see that for hydrazine and ammonia, we do get linearity in growth in thickness versus cycles. Where I wanted to point out, if you zero in or zoom in on that, you see that there's a little bit longer incubation time for the ammonia, where it took about 17 cycles for that growth to initiate. Looking at growth per cycle in the ALD window, I wanted to show just a direct comparison between the ammonia and hydrazine, where the ammonia is down here at the bottom. For ammonia at 400C, you see about a 17% decrease from hydrazine at the same temperature, so the growth rate is nearly 20% less. But more importantly, you see that it drops off significantly once you get down to 350 and then below on to 300, where basically once you get below 350, the reaction is incomplete and is not taking place entirely, leaving a lot of residual materials, which I'll show in a minute. Whereas the ALD window for hydrazine, you actually get an increase in growth per cycle, in going from 400 to 250, where these values are, still fairly good, even at, at all the entire temperature range. We see significant differences in refractive index of the materials. First of all, at 350 and 400, we see the refractive index of the hydrazine grown titanium nitride appears to be similar to titanium nitride grown by sputtering techniques as shown here. So we're hovering near that line for the entire ALD window. Whereas you see with ammonia, you're a little bit higher than the hydrazine in refractive index at 400 and a little bit higher still at 350. But once you go below 350, it raises significantly. And it's starting to, look more like titanium dioxide, where we attribute these high values to higher oxygen incorporation into the film, which is due to a lower reactivity of ammonia. Looking at the composition by SIMS, you see that ammonia at 400C has a pretty low chlorine content of about 0.88. Hydrazine at 400C is, in the same ballpark, maybe a little bit lower at 0.69. Where significant differences are seen when you go to 300C, where ammonia is at 7.46% chlorine versus the hydrazine at 2.09% chlorine. So this is that incomplete reaction that I mentioned in one of the previous slides. And then looking at the oxygen content, you see a significant difference in the films where the hydrazine films at 400 and at 300 are down around 4%. At 400C for ammonia, you see a little bit higher at 6%, and then ammonia at 300C is very high at 9.6%. And once again, this is reflected in, you can see this in the refractive index, as well as some of the resistivity that I'll show later on. We're able to achieve relatively smooth films with hydrazine, both at 400 and 300C, with a root mean squared of 1.5 angstroms and 1.36 at 400 and 300 versus 2.8 angstroms for the ammonia at 400C. So it's a little bit smoother film. We do notice crystallinity in all of the films that were grown. This is by XRD, where you see a little bit higher crystallinity in the ammonia film grown at 400, but overall you see pretty good crystallinity in all of the films that we worked with here. And finally, I'd like to come back to the resistivity and make a comparison to some of Professor Kummel's work. We did see the same types of properties that we observed with Professor Kummel. One of the key differences here is we did a little bit better on our resistivity of hydrazine at 400C versus the ammonia at 400C, where you see this is a little bit lower value. We also were lower at 300C, or significantly lower at 300C, where this got down to about 442 versus the 1240 for ammonia, where this ammonia was not quite as high as that observed by Professor Kummel. But overall, at 300C, you see a 64% improvement in resistivity at 300C and a 39% at 400C. So even if you were just to drop in and replace hydrazine in the current high volume manufacturing process at 400C, you still get a very significant improvement in resistivity. In summary, we've shown that the ALD window for hydrazine is about 250 to 400C. Where higher growth per cycle is achieved for hydrazine versus ammonia. This is significantly higher and could be important for high throughput manufacturing. We also saw a shorter incubation time for hydrazine versus ammonia, which could also lead to some of the better film quality that we see and better resistivity. We also see crystallinity in all of the films that were grown, where the impurity concentration of titanium nitride was decreased by using hydrazine compared to ammonia. And finally, we did see the much improved resistivity for films grown with hydrazine versus ammonia in the entire temperature range that we looked at. And with that, I'd like to thank you for joining and just thank you for your attention.